Hello, and a very warm welcome to this latest episode of Venena Mundi. In the two previous episodes, we found that the effects of harmful substances on the body depends on the type of exposure, the physical state of the poison or toxin, and its ability to be absorbed. However, these are only two pieces of the jigsaw. We now turn our attention to those substances, poisons and toxins which specifically enter the body through ingestion. In other words, by being eaten or drank and subsequently swallowed. What happens to these molecules once they get into the digestive system? What makes one substance so much better absorbed than another? And why is the digestive system so good at making a meal of such molecules in the first place? To find out, it's time for another episode of Venena Mundi. Let's begin by asking, why do we have a digestive system in the first place? It exists in nearly all multicellular organisms, from invertebrates to mammals and human beings, because our bodies are just too big to absorb nutrients directly from the outside environment, through the skin. Simple organisms can get away with this because they often swim in a liquid containing all the food they need, and this can simply diffuse through their outer layer. But this won't work for anything bigger, so these more complex organisms have had to evolve a digestive system, which is essentially a tube through the middle, through which the food can pass and where nutrients can be extracted. The situation is a little bit more complex than that, because food rarely comes in a conveniently reduced form. Animals, for example, hunt and eat other animals, which are themselves too bulky to be of use, so they need to be broken up into smaller fragments. Even then, the result may be complex food molecules like fats, carbohydrates and proteins, which are still too big to be absorbed. The role of the stomach, intestines and the other parts of the digestive system is therefore to break down the food, and even then into smaller molecules like fatty acids, sugars and amino acids. The process is called digestion. Once that's done, the next step to happen is absorption, where these much smaller and simple molecules are taken up into the body in order that they can be put to use, for example to provide energy or to build new structures. However, moving these products of digestion from inside of the digestive tract and through the walls of the intestines by absorption is a complicated process. In fact, 4 different absorption mechanisms exist, depending on a number of factors, including the type of food molecule being absorbed, its solubility, its size, and the part of the digestive system where the absorption takes place. Before briefly looking at each in turn, let's quickly see how the digestive system is optimized to make the whole process of digestion and absorption as efficient as possible. The first is to have as large a surface area as possible. Basically, the larger the area, the more space available over which absorption can take place. To achieve this, the intestine has a very highly folded interior. Moreover, these folds themselves have tiny finger-like protrusions called villi, which in turn are covered in even smaller projections called microvilli. Because of these, it has been estimated that the area of an average human intestine is about 250 square meters, or the size of a tennis court if all the folds, villi and microvilli are laid out flat. The second way of maximizing absorption is to minimize the distance molecules have to travel when they are being absorbed. Consequently, the walls of the digestive system are very thin, typically only 1 or 2 cells thick. Beneath them lies a very dense network of tiny blood vessels called capillaries, themselves also having walls 1 or 2 cells thick. Their purpose is to carry blood, which picks up the absorbed nutrients from the intestines and transports them to other parts of the body. Overall then, the maximum distance any molecule thus has to travel from the inside of the digestive tract into the blood is at most 3 or 4 cells. Between them, the combination of thin walls and large surface area gives rise to an amazingly efficient system for absorbing food. Bearing in mind that an average adult consumes about 4 to 5 kilograms of food and water per day, only about 300 grams emerges as waste. Now, we mentioned earlier that there are 4 ways by which these absorptions can happen. We will take a closer look at these individually in another episode, but for now, it's enough to say that molecules that are generally insoluble in water, such as fats and oils, and those which are particularly large, tend to be absorbed by a process called pinocytosis. In simple terms, the cell membrane in contact with the food folds and creates a small pocket which captures the extracellular fluid and any substances contained in it. The membrane then closes around this little pocket, forming vesicles, which migrate inside the cell. Here they combine with internal structures called lysosomes, which contain the enzymes that break down the molecules into simpler components. Not surprisingly, poisons and toxins which are poorly water soluble or consist of large molecules are also typically absorbed in this way. A second group of very specific food molecules, including ions, vitamins, sugars and amino acids, are absorbed into cells of the digestive system using active transport. This is necessary when the concentration of the substance in the cell is already high, and therefore the absorption needs to take place from an area of lower concentration to an area of higher concentration against a gradient. In effect, the substance is actively pumped across the membrane using special cellular mechanisms to raise the internal concentration still further. Since the molecules move against the gradient, energy is required to carry out this work. Not surprisingly, poisons and toxins which resemble vitamins, sugars and amino acids are also absorbed in this way. Finally, the remaining nutrients, specifically those which are small or water soluble or both, are absorbed by simple diffusion. It happens when a high concentration of a substance in a particular volume of space will spread out to equalize the concentration throughout the space if other areas in that space are low in concentration. The simplest demonstration is by adding a drop of food colouring to a glass of water. After a while, the colour will spread out throughout the entire glass. Exactly the same thing will happen if the concentration of a substance such as a toxin is higher outside of a cell than on the inside, and vice versa, providing that the cell membrane is permeable. The toxin will simply pass through in an effort to equalize the concentrations outside and inside the cell. Since membranes that surround cells have a fatty interior, it helps if the substance passing through is also fat soluble. Therefore, in general, molecules and poisons with at least some fat solubility will cross the cell membrane more easily than those that are just soluble in water alone. Okay, let's summarize what we've covered today. Fundamentally, in order for any substance to be absorbed easily in the digestive system, it needs to be a small molecule that's water soluble and preferably has some fat solubility as well. Such molecules typically pass through the walls of the digestive system very rapidly and do so by simple diffusion. That's why small water-soluble poisons are so dangerous. Other types of poison molecules, of course, will also be absorbed, but their mechanisms of absorption are much more complex and depend on how similar they are to natural nutrients absorbed in similar ways. For example, highly insoluble fatty acids are absorbed by pinocytosis, which means that similarly insoluble poisons such as phthalates also pass into the body in the same way. Fortunately, the absorption of such molecules is typically considerably slower, which gives physicians more time to take life-saving action. Of course, in tiny amounts, such toxins can accumulate in the body over many years unnoticed, creating a different set of problems, but that's for another episode. Meanwhile, at the end of the day, whatever the exact mechanism, the poison or toxin just takes advantage of a system already designed to make absorption of everyday nutrients fast and efficient. The poison just has to be present and the digestive system takes care of the rest. Okay, we've reached the end of this episode. Thank you for watching. If you liked it, please give it a thumbs up and use the comments below to say what you think or what you'd like to see in the future. In the meantime, don't forget to subscribe so I don't get lonely, and please click on the notification bell to make sure you don't miss out on the next episode. Bye for now, and see you next time.